Okay, yeah. Hello again, everyone. So today we are going to continue the pairwise sequence alignment problem, and I will go over this dynamic programming solution again and show you some examples. We usually don't do it by hand. We implement this, and I'm going to go over the C source code for that implements this dynamic programming solution, and we will maybe run it on some sample cases. Um, so let me also give you the right to participants, maybe anything info. If you're unable to write chat messages, maybe if I do stop sharing and here, yeah, participant. So somehow this assign privileges, all participants communicate chat with everyone. It should be available by default, but if you want to send your messages to be seen by everyone, please select everyone at the top of the list so that when you write something here on the chat box, everyone sees your chat messages. I had some problems in my previous courses, so the participants were not able to type chat messages that is seen by everyone. I was the only one seeing those chat messages, but if that's the case, please on the on part of these chat box, if you should be able to select everyone. It seems by default everyone option is selectable. Anyway, I mean, if you send sometimes they're not enabled by default. So if that's the case, I will try to enable it manually here. There was I looked at the meeting settings, and there is no such default setting to allow these things to participants at the meeting settings. You have to do it in the meeting real time. But anyway, if there are some such problem happens, I will do that manually. So let's get back to our problem. We are given two sequences, biological sequences that are like this. In the case of DNA sequences, we have two strings that in which the characters are from a 4-letter alphabet. In the case of amino acids, we have a 20-letter alphabet, the amino acids, and our goal is to relate these two sequences, to align these two sequences in such a way that every letter is going to be associated with either another letter, either another nucleotide in the other sequence, or a gap. Okay, and while we're doing that, our goal, remember, biologically, is to find the biologically most plausible relationship between these two homolog sequences. And the alignment programs, they're going to try to align anything that are given to them. So the program that you write that finds the optimal way to align them actually will not know whether these are homologs or not. Even non-homolog sequences, it's possible to align them. And if the result looks bad, it may be probably because they're not homologs. Okay. Usually these alignment programs, pairwise sequence alignment, they will be able to find the consort matching regions, insertion, deletion events accurately. But since they're guided by the scoring function that we have, especially in protein sequences, the scoring function, which scoring matrix we use, what are the gap insertion, gap extension penalties, these really are important parameters that guide the result. So you may use the default parameters that I mentioned earlier. So if you remember, we talked about these, and these are the typical scoring matrix input values that we input to our pairwise sequence alignment algorithms. Now, I'm going to describe the dynamic programming recurrence relation again by trying to find a solution to this one. All right. Now, if you look at this alignment, and we are again thinking about the global pairwise alignment in which all of the letters have to be assigned to something. Okay, we are not ignoring any part of the sequence. When we are ignoring some parts of the sequence, it may be the last column in the alignment may not contain these last two nucleotides. But if we're doing a global sequence alignment, all the nucleotides are aligned with respect to each other. All right, so if you in any of these alignments, whatever, if you look at all possible alignments, which are exponential in number, if you remember, we talked about this, the number of possible paths from the left, top left to bottom right, it's exponential in number. But considering all possible alignments, the last column, if you consider the last column of the alignment, this C, for example, is either aligned directly against this C. So the last column of the alignment is either this or that or this, okay? This one, again, the first sequence, second sequence, first sequence, second sequence, the first sequence is at the top. So the last column of the alignment has to be one of these three things. Okay, there is no other option. Can you write me any other option other than these three things? The last two correct characters are here, CC. Okay, it should either be this or there's a deletion of the. I mean, there's this is like an insertion in the first sequence, or this is like an insertion in the second sequence. There is no other possible way to write the last column of the alignment. Okay, so these are all the possibilities. Now, if all the possibilities are these, which one of these three options is the best option? Is simply is what we are doing in this dynamic programming recurrent installation. We check, okay, if this is the case, if we choose this option, then the score has to be a match of C and C, a positive score, plus the score of best way to align the first part here, whatever the score of best aligning the first n-1 characters to m-1 characters here, that ends at C and A, okay? Let's call ends with this. So let's, for example, I don't know how many characters are there here, but basically the score plus score of two short sequences. Okay, which are, when I say short sequence, it's one nucleotide short sequence. Okay, it's the score, the best way, the score of best way of aligning the first part and this part. Now, actually, in order to describe this score in a better way, not in English, actually, we have defined a function last time, which is this. Fij is the function that shows the score of best alignment that aligns the first I character of the, it's like the prefix of the sequence, which contains the first I characters, align with the first J characters. This F function, let's define it as the score of the best alignment. Okay, we are going to keep track of this. And we are looking for example, let's actually count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5, 20, 25, and 30, 31 and 32. So n is equal to 31, m is equal to 32. We have this many characters here. Okay, now here the first option, now I can write, since I defined that Fij, the first function will simply be this one. Okay, F30, and the score of aligning the first 30 characters against the first 31 characters of the second sequence. If I match this, if I choose this option. If I choose the second option, its score will be a matching of C against the gap. Okay, because it means that the score of, so this first part is the score of just individual column. So the score of individual column will be matching C against the gap, which is actually the gap penalty. I can directly write here the gap penalty. The gap penalty plus what is now the score? What will I write here inside this F function if I choose this option in lines 13 and 14 here? Any answers you can write in the chat box. If I use exactly, so it's going to be 30, because this let's it's whether it's going to be 30, it's just not going to be 30, it's going to be 30 and 32, right? Because I still have, if I put gap against this one, so this one has a gap against here. It's like this. The alignment is going to be something like this. Okay. Now, this is the last column. And the first part of the alignment contains 30 characters of the first sequence, and the 32 characters of the second sequence is already there. They need to be aligned. So it should actually be 30, 32. Okay. Now, and the third option, our third and final option, will again be a gap penalty plus f, this time 31 and 31. Okay, you see why this is 31, 31, because the first, now I'm looking at this option. The final option is this. There's a gap against this one, and I have 31 characters to align still on the left-hand side to align. And this one, the second one was 32. Now it contains 31 characters on the left as well. So 31, 31. Look at this. Look at this. When I'm, in order to figure out, so I have these three options. Which one is the best way? Which one is the solution? The one which is largest. Okay. So basically what we do in this dynamic programming solution is that we don't actually know which one of these options is the best one until we compute these three things. So we compute these three entities. In other words, F31, 32, which is the final result of the alignment, the optimum score of aligning first 31 characters against the first 30 characters of the other one, which means that the complete alignment is the maximum of these three options. Maximum of this, the other, this one, and this one. So we look at all possible cases. So it's impossible to miss. So this the best way. Okay, if you write it like this, you're looking at all possibilities. Therefore, this is not a heuristic. This actually guarantees the optimal solution for this. By the way, I'm recording. Okay, so if you look at this, if this is ij, so in other words, if I can generalize this to have fij is equal to either the maximum of the matching of whatever the ith character in the first one and the j character of the second one is, plus I match the ith and jth characters, and then I look at I minus 1, j minus 1. This is the first option here. The first option that I write here corresponds to this one in general, or a gap plus f I minus 1 j and a gap f I j minus 1. Okay, so this is the general recurrence relation that I come up with when I'm solving this problem. Now, since this is as you can see, in order to find this, in order to solve this, at this point, for example, can you know which one of these is the best option? No, because we don't know what F30, 31 is. What is this? F30, 32, we don't know that. We need to keep solving this. So we are going to ask the same thing. So for F30, 31, what is it? Okay, so I'm going to, F30, 31 is the match of whatever A30 and B31. Actually, I should have, not A, this is the second sequence. You should have corrected me. So if A is the first sequence, B is the second sequence. This is the ith character of the first sequence, jth character of the second sequence. These are two different sequences. So B31 plus F29, 30. So it's going to keep increasing like this. If you implement this recursively, you may imagine that you will have to call an exponential number of f functions until you reach f00. So f00 is one of the base cases, which is 0. What is the score of aligning the first zero characters with first zero characters of the second. So this is like the score of an empty alignment. So this may be when we hit F00, there is no need to call recursively. So this recurrence relation has a base case, which is this. Other base cases that I can think of are this. For example, if I have Fi0, what does this mean? What is the score of aligning the first I characters to an empty sequence? The only way to align the first I characters to an empty sequence is, so let me write the exact sequence. For example, if these are the first I characters, okay, if I is this, the only way to align these first I characters against the first zero characters of the other sequence is to put this many gaps, okay? Exactly, so it's going to be, thank you, it's going to be I times gap penalty. And again, this I indexing starts at 1. So I call this is the first character is, for example, F11. What is F11? Is it A and T aligned with each other? Actually, I can have many different things for the first case as well. A and T may be aligned each other. It may be A against the gap, T against the gap. So I may have different options. But here is, let me write my base cases. Similarly, I will have 0, J. These indices are arbitrary. You can use the same indices, but these are my base cases where I don't need to think too much. All right, I just need to just if somebody asks me what is the best way to align the first I characters against nothing, the only option you have is to put gaps. Okay, so these are trivial solutions that you don't need to call F recursively on again. All right, so these are our best cases. So in other words, in order to find the final solution F3132, you need to call recursively like this. For example, F3132 makes these calls. F31, then F3131, and F3032. Okay, so these are the three calls it makes. This function is going to need these answers to be able to choose the maximum of them to find its correct value. And this one needs F29, 30, F3030, and F29, 31. Okay, so these are the three things. And this one is going to need F3030. So if you implement this as a recursive function in your code, as you can see, the branching factor is 3, and we are going to get to the end of F00 at roughly at depth 30 or 31. So the number of function calls you will be making if you implement this recursively is going to be exponentially large. So dynamic programming is a technique to avoid this many exponential calls. How can we avoid it? Look at some of the recursive function calls. I mean, the recursive, if you write a function recursively, the recursive function calls are actually very dumb. I mean, they don't know whether certain values previously computed too. Now, look at this here. Look at this F3030 here. I have exactly the same thing, right? F3030. So whatever branch I have here is going to be an exact replica of this one. And if you implement it recursively, you will be wasting the exact same amount of computation time you require to compute this. You will be wasting it again for this one. And it may appear in many different places. So the idea of dynamic programming is converting a recursive solution to an iterative solution by storing these computed values beforehand in a table. Okay, so in the term programming actually refers to some tabulating, putting certain things in a table. It has nothing to do with C programming or Python programming or Java programming. Okay, so in dynamic programming, the term programming has nothing to do with programming. The term programming these days, it was used to as a tabulation, to indicate tabulation. So what we are doing here is that we are building a table dynamically. Okay, we build a table dynamically as new information is available. We put entries into the table, which we call the partial solutions table or partial scores table. Keeping up this, building this table and making sure that these redundant recursive calls are not called multiple times helps dynamic programming to run really efficiently. There are two ways to actually avoid redundancy. One of them is, instead of having these recursive calls in a top-down manner starting at F3132, building the entire thing bottom up by building a table. That's what dynamic programming is. We are going to build this entire table starting from the first trivial things that are available, F00, Fi0, F0J. So we are going to fill our table starting with those and then build these solutions bottom up. If there's any intermediate node here for which all three child nodes are known, if we know all three of them, then we'll be able to complete this one. So this will be like filling this. This is how we are going to fill the table and find the values of these things bottom up. This is what dynamic programming does. Okay, another alternative, anybody knows the other alternative, what we can do? We can actually still do the top-down solution starting here and make recursive calls. We can implement something recursive, but we can put a little bit intelligence to our exactly. We store, does anybody know the name of this algorithm? Storing the computed values in some kind of a hash table or in some kind of a table in which you're going to look up. For example, when you call F3030, if somebody else wants to call the F3030, you don't do that. It's called actually memoization. If you have heard this term before, it's very similar to dynamic programming. They usually go hand in hand. It's not memorization. This is not. Sometimes you can actually. That's also true. Tail recursive. If the recursive calls were at the end, you're also able to convert it into an iterative program on your own. You can do that. You can convert recursion to an iterative program. That may also work. But to actually store, even this memoization works for cases where you still have the recursive implementation. You don't need to apply these tricks to convert it to an iterative algorithm, but you store basically these pre-computed values. And if some other recursive call needs this, it looks into this cache that contains previously stored values, and that's what memoization is. So in this course, we're going to learn speed up computer programs by storing the results of expensive function calls and returning the cache result when the same inputs occur again. So it's very similar to dynamic programming, but we can still do top down. Okay, they are similar. Now let's get back to our solution, and here, this is the solution that I wrote on the notepad. Here is written on the slide too. If these are my base cases, the score of aligning against gap, the recurrence relation is this. Whatever the gap penalty is. So this is written as a summation here for all characters align against a gap. But this is basically the gap penalties. And Fij is the score. This small s is not a recursive function call. It's a lookup table. So this small s is our scoring input, scoring matrix. What is the score of aligning a gap against the jth character? This lookup is going to tell us, oh, it's the gap penalty. It's -1 or -2, whatever it is. Okay, so this is these are the gap penalties, and this score of aligning the ith character against the jth character. Again, this is not an alignment problem. This is this small s function is our scoring function, which tells us whether it's a match score or a mismatch penalty. And for amino acids, it's going to tell what is this. It's going to be a lookup to that 20 by 20 table, which shows the score of aligning a particular specific amino acid to another specific amino acid. All right, so basically this is the entire solution. Now, if you look at what we are going to do here, if you look at this table, basically when you implement it, you write an iterative program for the solution. Let's actually directly now go and take a look at the code, how we implement such a dynamic programming solution for this problem. Here is the code that is available on the course website. Some of the things are hard-coded here, like the strings, the character arrays. They have a maximum length of 501. I didn't use dynamic arrays, they're just constant arrays. So if you want to align longer sequences, you may need to change these constant values. And we have a linear gap penalty, -2 per gap, a match score of 4, and a mismatch score of -3. And this is, for example, if you're going to use protein sequences, you may need those scoring matrices that show different scores for different amino acid pairings. Now, what we need is a max function. So this is pure C. Some of the functions that are available in C++ or STL are not used here. It's really very simplistic manner. So finding the maximum of 3 things. So we write something here in terms of equalities. So this is going to return. In terms of equalities, it's going to favor the first option. Okay, and so this is the maximum of 3 numbers. What is this Tmax? We are going to come to that later. I haven't mentioned that because right now we are finding the score only. Okay, if you implement this dynamic programming recurrence relation, at the end you're going to find a score that says, actually, let's first focus on that part. Let me just copy this to align. I'm going to call it align score only. Okay, so let's get rid of the unnecessary parts here. So match and mismatch are the penalties, mismatch penalties. So this append, I don't even need these parts. So I'm not only interested in the score. The resulting alignment, I'm not interested in this one either. The traceback matrix, I'm not interested in this one either. Now we open our input file. We read the 2 strings, we output them to the user, we find their lengths. Now, here's what we do. This is, we initialize our table. This S is that F table. Okay, let's rename it as F here in this case. Okay, so we have our partial scores table that we are going to build, the F matrix. And I initialize F0020, and whatever the gap penalty is, I also initialize that one to gap times whatever the gap penalty is times I. So these are my base cases, as you can see. I start filling in the table. These 2 for loops fills the entire first row and the first column. The top left entry is filled with 0. And here is what we do. These 2 for loops, let me delete this one, and F. If you look at this code, it's exactly the same thing as the recurrence relation on the slide. The score is this. All right. So let's forget about the remaining parts. We are going to come to that later. All right, so it's a really short code. As you can see, it's really simple to implement this dynamic programming solution. Align score. So it starts at cell 1-1, and we can either go row by row or column by column. It doesn't matter. When we are filling in this cell 1, 1, 1, 0, 0, 0, 1, 0, and 0, 1 are already computed. All right. So if you go row by row when you're filling in this table, if you go row by row, as you can see, while you're filling each entry in a row, these three elements to its diagonal, to its top, to its left, they will be filled already. So you will be able to fill in all these entries row by row. You could also go column by column. As you fill a column, it's these three neighbors. These three neighbors are the three entries. If I'm going to fill the cell under this hand, these are the three entities in the recurrence relation. All right. Now it's basically fi minus 1j minus 1, fij minus 1, and fi minus 1j. This is really important. Usually when students fill these by hand, they forget to add these gap penalties, or they forget to add these match score, and they just think that while we're selecting the best option, we just select, for example, what are we going to put here under this hand? They just directly look at these three things, whichever is maximum. -2 is maximum, so let's use max. -2 plus gap. Actually, we don't first select the maximum and then add the gap. It's like we first add the gap to this one. We need to add the gap to this one as well. And we need to add the mismatch penalty or match score to this one. And we compare those three values. Whichever is maximum, we write it here. And after that, after we compute the final value at nm, we print it out. Okay, so let's run this. This is a really short code. Let's compile and run it. So it was in the desktop. Oh, sorry, I have to go to the Windows. It's lowercase. So I'm using Windows subsystem on Linux. I have a Windows machine here, but I'm using Linux installation on it, Ubuntu, to compile and run these things from the command line. Here's my desktop. So it was a line score only, this one. So let's compile it. So this exit function is an stdlib.h. I forgot to, so it's a warning, but let's get rid of this warning as well in order to exit from the program prematurely. Okay, so it compiled. Now when you run it, align score, it requires an input file. We have the input.txt. So when we run it, the score of the alignment it's really fast. As you can see, there are 30, 31, those exponential numbers. The score of aligning these two sequences is 68. It was very fast because it runs in polynomial amount of time. We can give it very long sequences. For example, let's just choose random DNA sequences and CBI gene bank, or let's go to NCBI gene bank and let's select some random sequence, or I can do something else randomly. Input2.txt, because I just want to do some things randomly. So I have my 4 fingers. Oh, some of them, or I need to make sure I hit the shift. Okay, so this is just a random sequence, a very long one. And the second line, I have the other sequence. Yeah, I need to press shift. So these are just 2 random sequences, not homolog at all. Okay, so just random. Oh, there's a small g there. It doesn't matter actually. If I have some errors in this capital, yeah, there's a small g in the first one too. It will just be a mismatch, and that's okay. So yeah, so shift. All right. Wow, that's really interesting. Even if I'm pressing shift, sometimes if you press the others fast enough, The shift can be just ignored. Anyway, so these are just random 2 sequences. Let's run our program with the second one too. Now the score is 78. Wow, interesting. It's what is interesting is that just even random sequences, you get some scores. Okay, now in the next week, we are going to talk about, okay, this score 78, what does it mean? For example, what is if I had 2 random sequences of length 80, 100, if they were random, what is the expected score between them with this match mismatch scores? Because since I only have 4 letters, it's still possible to align them, right? So even the random sequences could be aligned, but maybe if they were really homolog, they will, for example, if let's look at input 3 and let's again enter these long sequences, this time with all A's in one of them and all A's in the other. Let's see a large score we can get with these long sequences. Input 3. Yeah, you see the alignment score is now 390. So a random sequences could get 78. 78 is it a positive score? All positive scores are bad is not a correct statement. So we are going to talk about the statistical significance of alignments, and we will convert these raw scores into E values or P values. All right. So anyway, what is missing from this alignment is that, I mean, even we're just outputting the score, right? You're not outputting anything, the alignment itself, which is where are my gaps? This is just the first sequence and the second sequence. This doesn't report the final alignment. The parts that I deleted from the source code was actually reporting the alignment. So how can we report the alignment, whether there's a gap, whether there's a match or mismatch? The way we do is like this. Every time we have that information, whether there should be a gap or there's a match, while we are filling this table. For every choice we make, for example, when we are filling this cell, the entry in this cell, whether it's computed, it's filled in by using the one on the left, the one at the top, or this diagonal entry, tells me what I'm doing by moving from here to here. For example, if I use this -2 to find the best way to align the P with an E, it means that I consumed an E here, but I'm still at P. Okay, I'm still at the same column. So moving right here, if I make choices that will make me fill these entries by using the values on the left, it means that I'm putting a gap against the character that is here, E against the gap. So what I need to do is, after I compute the best score, after I find the best score, I need to trace back the entire table to this top left to question my choices, to see what did I choose to come there. For example, for the last entry, if you have chosen this diagonal here, it means that this E is aligned against an E. That's what we call the traceback table. Whenever, actually, either you can do it after you fill in the entire table, you can write another for loop to figure out which ones actually you used. But while we are filling the table, we already have this information. We already have, when we are choosing the maximum, we actually have the information which maximum was chosen. If the maximum on the diagonal was chosen as the maximum, all I need to do is, just like Hansel and Gretel in their story, where they're putting breadcrumbs to find their way back, I'm just going to put, for example, for this cell, I'm going to put something that says diagonal. I came here from the diagonal, and I came here from the left. I came here from the top. So if I put these single character labels, or you can use just integer 0, 1, 2, you can use any coding you want. Now, but if you just indicate which one of those maximums, which one of those 3 options was chosen as the maximum one, you'll be able to start from this last entry and go all the way to the beginning by, okay, for example, if you see a D, that breadcrumb D that tells you came here from the diagonal, you will move here. If it says up, you'll move here. So it will trace your path back to the beginning. And while you're tracing your path, You can build the actual alignment, the output, by putting gaps or matching the characters if you use the diagonal, by putting a gap in this second sequence if you're moving up. If you're moving left, you're putting a gap in this sequence. This is what that other code actually did. Let me open that code and show you how I did it. It's this one, the original one. So what we do is this tmax actually is just putting the table whether based on the option we have chosen, whether it's a diagonal. This is the breadcrumb that we're putting on that second matrix. So in terms of space, we double the space. We have this traceback matrix that we maintain. This was that matrix, traceback matrix, which is exactly the same size of S and T, and it's a matrix of characters. I'm going to put these as my encoding. I just use the characters D, L, and U to make it more readable for whoever reads this code. And what basically we do is, as you can see, whatever is chosen as the maximum, this one also chooses whichever is maximum. This Tij will be filled in with the corresponding character D, L, or U. And after the entire table is filled, I process the traceback matrix starting from the bottom right row, so starting at N and M and going all the way to 0, 0. Both of them have to be 0, 0 until I reach the table entry 0, 0. If the current entry is D, what I do is I decrement both of them, and I maintain a string that I built the alignment starting from the last character. So I append a new character to the beginning of this. So this appends some letter, some character. This is a single character to this one on the left. So this is my resulting alignment. All right. And if they are equal to each other, I append the alignment information that is shown in the middle shows whether it's a match or a mismatch by using two of these special characters. All right, so I can actually directly show you the result to see how the alignment is shown. Let me go back to Ubuntu and let me compile the original one, and let's see when we align. Okay, again, there's this warning. stdlib, I forgot to include this. So when I run a line in my input.txt, you see the score of the alignment is 68, and this is the alignment that gives 68. As you can see, there are gaps. There's 4 gaps here, 2 matches, another match. These are the gaps. T and C is a mismatch. So I start building the alignment by going over the traceback matrix from right to left. And as you can see, the alignment is shown correctly in a sense that, I mean, the size of everything is matched against a single thing here. When I have a match, it's shown here. I have this many matches, 2 mismatches, T and a C mismatch, T and a C mismatch here, and the others are matching like this. So if I run the same thing for input 3, you're just going to see all matches everywhere. As you can see, it doesn't fill, the entire alignment doesn't fill in the screen. So you have to do some additional coding if you want to divide it to chunks of 80 characters each. Usually programs that show alignments, long alignments, they provide the page on a page. In order for them to fit on a page, they show them like this. So the first sequence was the longer one. Therefore, we have to have gaps at the end of the second sequence. What about this other one, which was random, input 2? Look at this. This is my random alignment with lots of gaps, but it still have lots of matches. Okay, it's possible to do. It's random, but it's possible to have a lot of matches here. That's why it's like 78. Anyway, so that's basically the pairwise sequence alignment. So before I stop today, so this is an example of a filled-in table for 2 protein sequences. This link is probably outdated, but if you search for NCBI, probably has some applets or tools that show these alignments on the web. You can run certain alignments on the web and see the results. You can also try this code that I just provided on our course website. There are certain versions of these alignments that we're going to talk about on Monday, which is the semi-global alignment and local sequence alignment. So sometimes we try to align a short sequence against a very long DNA sequence. For example, imagine we have like a 4,000 base pair, maybe it's the DNA sequence of a gene, a small gene, and we want to compare it against the entire genome of an organism, yeast genome. And what if only a certain portion of this, for example, maybe it contains a domain inside it, 1,000 base pair long, a certain pattern, only that pattern, 1,000 base pair long region inside it is similar to another 1,000 base pair region inside this whole genome. If we try to use the algorithm that I just gave, the global sequence alignment, we have to first of all pay lots of gap penalties, right? I mean, this is 4,000 characters long. This is 12.5 million characters long. You have to put, in order to put some gaps against millions of characters here, you are going to be paying lots of gap penalties. One option is maybe if there are gaps that appear at the end of the alignment. Okay, if there are gaps that appear at the ends of the alignment, maybe let's not penalize them. We may ignore to penalize the gaps that are at the end, because when you're aligning a short sequence against a large one, you're bound to have gaps for any alignments will have these gaps. So we may say that let's not penalize terminal gaps. Now, here's a question before we end. What modification do we need to the original dynamic programming recurrence relation that we gave here? What modifications do we need to make it semi-global alignment? I don't want to penalize the gaps at the beginning or at the end. So we may try to answer this on a table. This is the dynamic programming partial scores table. I have 0 here at the first row. Now I'm going to, the sequences appear here, for example, G, C. So my question here is, if I don't want to penalize the terminal gaps that appear at the beginning and at the end, what kind of a flag? So how am I going to fill in this table? Just think about it. So there's a question by Marta. I'm going to read that later. So I'm going to get your question later, but let's think about, yeah, actually, if something is below 0, we can make it 0 is actually the answer to the local. It will give a local alignment. It will not only, I mean, if we have a solution that says if something is below 0, let's make it 0. It will also have the power to ignore different parts of the alignments. You will have, for example, if the semi-global alignment still tries to match the entire smaller sequence against the other one. We're just ignoring the terminal gaps. So you may actually have some negative score at some place. So you cannot ignore that in semi-global alignment. So one thing that is obvious is the first row and the first column has to be all zeros, right? Because what is this first column and first row? I mean, these are like an initial terminal gap at the beginning. Okay, so terminal gap at the beginning against the first sequence, or terminal gap at the beginning against the second sequence. So these are going to mean that. Now, is this sufficient? This modification, just putting zeros here and treating we need something else, right? It's not sufficient. We need for the ends. Yeah, how do you implement? So should I put all zeros at the ends here as well? Which will make it incorrect, I guess. This is not This shouldn't be the case. I mean, if you put all zeros, what if I have some negative values here, or maybe I had some positive values? What if there's a path that comes here and it has some positive value, 34? Making it 0 is just really penalizing it even more. So it's not, the answer is not, the solution is not to put all zeros at the columns. We can extend the table maybe, but the actual answer is very simple. So it's, for example, what does a terminal gap here? For example, oops, I accidentally deleted the entire table. So for example, if I have a value here, 25, and for example, if here is 12, and maybe here is 26. Yeah, exactly. That's the correct answer. When we come to the, so for example, what I want to do is, for example, a gap from here to here has to be penalized, but going down in the last column should not be penalized. You should be able to use 25 directly here, or when you're in the last row, similarly when you have a 25 here, you should be able to. So in other words, the only modification we need to do is put these zeros at the first and column and first row and move freely without penalty to right on the last row and down on the last column. So moving down in the last column does not have an associated gap cost, and moving right in the last column does not have an associated gap cost. So this means terminal gap against the second sequence. So this is a modification that we can do for what is called a semi-global alignment. We are still trying to align the entire sequences, but when gaps appear, we can only move right and down. Yeah, exactly. From here, you can only move right and down. But for example, what I mean is that this entry here, it's possible that we fill it either by using this one or this one. This entry here, for example, is not certain that you're going to get to this entry from the left. Okay, these paths are still possible. So we cannot just, when we find something here, 5 for example, you shouldn't just write 5, 5, 5, 5 all the way to the end, because these paths are possible. The only thing is that if this option here has the freedom to avoid the gap penalty, the others are going to have the penalties, match, mismatch scores coming here, and gap penalty if you move from here to here. But moving right on the last row has no associated gap penalty, and moving down in the last column has no associated gap penalty. So this modification changes the way our algorithm works. It will no longer penalize gaps that appear at the terminal ends of the alignment. All right. And what Ogin actually told that when something drops below 0, replace it with a 0, solves another interesting, challenging problem, which is this local sequence alignment. Okay, so we'll be able to solve local sequence alignment, meaning that we'll be free to start the alignment anywhere within the sequences. We'll be able to ignore the prefixes and some suffixes of the alignment and find the local region with the maximum possible score. So and this modification, just when something drops below 0, choosing the 0 is not the only thing we need. Actually, we also need to, the local sequence alignment result is no longer necessarily at the bottom right of the table. We are going to look at the entire table and pick the maximum number in the entire table as the end of the alignment. All right, so we're going to talk about this on Tuesday. When does this local sequence alignment found? We need local sequence alignment when certain homolog sequences share only local regions. For example, there may be 2 protein sequences which may be related in only partially. A certain biological domain, a small domain sequence may be similar in the other one. And if we try to globally align them, we will never find that highly matching sequence, because we will need to pay lots of mismatch penalties elsewhere. The global solution that tries to optimize the entire thing may miss that highly conserved small region. If you're sure that there's a small region that is possible in both cases, we actually do a local sequence alignment. So there's a biological need for trying to align sequences locally when for divergent sequences, for sequences that certain parts may be divergent, they're different, they may have different functions, but a certain small region may have an important conserved function. In order to be able to find those, we may need to perform local sequence alignments. We're going to talk about the details of this local sequence alignment on Monday. All right, and I will show some more examples, and then we will conclude sequence alignment topic. And so Mert, yeah, thanks a lot, Ege. Yeah, I forgot about Mert's conceptual question. Thank you very much. So yeah, I totally forgot about that question. So in the second code, we calculated the scoring. We saw based on biological initiating a gap has a, so in all the code here, we have seen here, in both align score and align C, we are using a linear gap penalties. So initiating a gap and extending a gap has the same penalty. But in all of these scores that we use, they have some biological background, especially, for example, whether if in nature we observe, as just you said, initiating a gap has a higher penalty than extending a gap. They all come from biological observations. If the scoring were different, we would definitely get different alignments. For example, if I just change, for example, match score 1, mismatch score -30, it will be really different, okay? Or the difference between mismatches and gaps, for example, it will probably, instead of having a mismatch, it will just put gaps. Probably if I do something like this, we will never observe. For sure, that's a certainty actually. If I have a mismatch score of -30 and gap -2, having a mismatch, we will never have a mismatch, because look at this. This is a mismatch, okay? Look at this mismatch, -30. You will just be replacing it with this, which has a score of -4, okay? So 2 gaps, -4, much better than a mismatch of -30. So these the scoring inputs influence what you see. Therefore, defining these score parameters, scoring matrices, especially in protein sequence cases, these scoring matrices have tremendous importance on what we get as a result, because the algorithm does not really know which one is the best way to align. It's just a mathematical. It's just a program and finds the optimum way of aligning them given the scoring matrix. That hence determining these scoring values to best match our biological observations is a very important and crucial thing. And that's why those scoring matrices required lots of research efforts to come up with in 1970s, 80s. All right, I hope this answers your question. You would definitely get different alignments if the scoring is different. All right, any other questions? I will stop the